Good morning. My name is Timothy Bilton. I'm a scientist from the Bioeconomy Science Institute, formerly known as Ag Research. And today I'm going to talk to you about a really exciting research project that our research group has been working on the past 3 years or so. And that is to develop and test portable accumulation chambers, also known as PAC, for cattle to measure methane emissions. I would like to acknowledge Suzanne Rowe, who is the driving force behind this project, and also to acknowledge our industry partners. So why are we interested in developing PAC for cattle? Well, in sheep, PAC has been highly successful for measuring methane, and we now are collecting over 5,000 commercial measures a year in New Zealand. We do this using 2 trailers that have 12 PAC units on them and transport them around to farms across the country. And the great thing about PAC is that it is suitable to rank animals on their methane emissions, which then enables us to generate methane breeding values for the farmers and for the industry. However, the original PAC units were designed for sheep and are too small for cattle, and there are also limitations of measuring methane on farm for cattle using other technologies that are currently available on the market. The really nice thing about PAC is that it is relatively low cost and only requires a 1-hour measure. And for cattle, we have been measuring animals in groups of 4 to 6, which enables 32 to 48 animals to be measured per day. The pictures on the slide show the chambers for cattle pack. The picture on the bottom left is the chamber, the cattle pack chamber, and on the bottom right is the inside of those chambers. And the picture on the top left is a manometer, which we use to measure the pressure in the chamber. And on the top right is an Eagle analyzer used to measure the gases in the chamber. Now I'd just like to show a video showing the cattle pack setup. So the protocol for cattle pack follows very similar to the protocol for sheep pack. First starts with the animals being brought into the yards, and then we weigh the animals and we make sure that they're at least 1 hour off feed before we walk them into the chambers. We make sure that animals are settled, and then we close the doors at either ends. And the animals are in the chamber for approximately 50 minutes, where we collect measurements at the beginning, at the middle, and at the end of that 50-minute period. We use an Eagle analyzer to measure the gases inside the chamber, and we also use a digital manometer to measure the pressure as well. And at the end of that 50-minute period, the animals are released back onto the pasture, onto the paddocks. Now you might have noticed or wondered why the chambers are quite tall, because they are quite tall. This is because we need enough volume in order to get good estimates of the gases inside the chamber. And the other thing to note is the chambers do weigh around 500 kilograms. They do have hooks on them, so they can be picked up and moved with a tractor fairly easily. So we've used the cattle pack chambers to measure methane emissions in some beef animals, and the table here summarizes the data we've got to date. We have 4 cohorts of approximately 120 to 130 animals, consisting of either Angus or Hereford breeds or crosses between these 2 breeds. All the animals were 1-year-old heifers, except for cohort 3, which had some steers. The first 2 cohorts also had 2 PAC measures taken approximately 2 weeks apart. And in total, we have 500 animals measured, with approximately 740 PAC measures in total. The average live weight of the animals ranged between 250 and 280 kilograms. And cohort 2 and 3 both had feed intake data collected, which enabled us to estimate methane yield for those cohorts. On this slide, we have some summary plots of the PAC data we've collected in the beef animals. On the left is a histogram of the CO2 levels, and we look at these because it's important for animal welfare and health reasons. We need to make sure that the CO2 levels do not get too high. And for the data we've collected to date, most of the levels have been between 1 and 3% carbon dioxide. On the bottom right, we have the methane grams per day trait relative to the time that animals had been off feed before they entered the PAC chambers. And as we expected, the methane levels drop the longer the animals have been off feed, and this is something we see in sheep. This also suggests that appropriate scaling is required, as we do in sheep, and something that needs to be considered when analysing cattle pack data. If we also look at the mean methane levels relative to the mean live weight of the cohorts, which is shown in the table at the top, we see that those are fairly consistent across the cohorts and a little bit larger than what we see for sheep. We then proceeded to estimate repeatabilities and heritabilities for our cattle pack traits for these beef animals. And the table on the slide here summarizes our results. We have 4 traits that we looked at. The first is methane grams per day. The second is methane yield. The third is a methane ratio trait, or methane over total gas, which we use as a proxy for methane yield. And then a carbon dioxide, or CO2. And as you can see, the heritabilities range from 0.1 to 0.15 for the methane traits and was 0.5 for carbon dioxide. And the repeatabilities range between 0.3 and 0.4 for the methane traits and 0.5 for carbon dioxide. Just want to note that for this analysis, I included pedigree for the genetic component, and I also included the time the animals had been removed from feed into the model to account for how the methane decreases with the amount of time they've been away off feed. We have also used cattle pack to measure methane emissions on some dairy heifers, and the table on this slide shows the data that we have collected to date. Again, we have 4 cohorts, where each cohort has between roughly 90 to 105 animals, with all but the first cohort having 2 pack measures, again 2 weeks apart. The average live weight of the cohorts ranged between 208 and 307 kilograms, and was larger in the later cohorts because these were measured later in the year, and so the animals were a few months older. All the animals were measured when they were part of a feed intake trial, and so we were able to estimate methane yield traits for these animals as well. We also estimated heritabilities and repeatabilities for the dairy heifers, and the results are summarized in the table on the slide. As you can see, for the methane grams per day trait and the methane ratio trait, the heritabilities were similar to what we had in the beef animals, but for the methane yield and for the carbon dioxide, the heritabilities were a bit lower than what we had in the beef animals. We also found that the repeatability estimates were lower than what we had in the beef and sit at around 0.2 to 0.3. I just want to note though that for this analysis, I scaled the traits by the pack lot instead of using the time off feed information into the model directly, and I think that might have resulted in lower heritability and repeatability estimates. And I also use a genomic relationship matrix for the genetic component in the models. So one question that we have been trying to grapple with cattle pack is how many chambers do we need for a collection? And to answer this question, what we have done is to do an analysis using pack data that collected from sheep, where 12 chambers are used, and performed a simulation study whereby we randomly split the data into smaller lot sizes and re-estimate the breeding values. As part of this analysis, we have also investigated different approaches to scaling the data. Typically in sheep, we scale by the lot mean, but we have looked at using time off feed information to scale the data instead. We then compared the breeding values from using smaller lot sizes, as given along the x-axis of the figure on the slide, and different scaling methods, which are represented by the different lines and colored points, relative to scaling using the lot mean, the standard scaling method with 12 chambers. And there are 2 main results that I want to draw your attention to from the study. The first is that when the number of chambers drops to less than 6, there is a noticeable drop-off in the breeding value correlation compared to 12 chambers with standard scaling. From these results, we recommend using a minimum of 6 chambers for a cattle pack collection going forward if possible. The second main result is that when there is less than 6 chambers available for a cattle pack collection, using the time of feed information for scaling seems to provide better performance. So in conclusion, we have successfully developed and tested PAC for cattle, and we have got results that look similar to what we see in sheep PAC. And also too, we found that cattle pack traits are repeatable and heritable, which is important going forward for breeding purposes. We also recommend 6 cattle pack units to be used going forward for pack collections based on our results that we have to date. We also have a number of ongoing work in this area. So one is that we have some green feed data that's been collected alongside some cattle pack data, which we want to use to help validate the cattle pack more. We also have in the pipeline the development of a larger cattle pack unit, which we want to use for lactating cows and larger cattle animals. And we also have a number of programs going forward for funding more pack measures, particularly in beef. Lastly, I'd just like to acknowledge our funders and the organisations that provided animals and helped with collecting the data, and also to acknowledge those who helped out with the early development of the cattle pack chambers. Thank you very much for listening.